The next type of simple harmonic motion we want to look at is pendulum motion. All a pendulum is a mass suspended from a pivot point by a light string or a rod. So, quick diagram of what this looks like. Pendulum, and then it's going to swing back and forth. And I didn't show it at the rest position. The rest position for a pendulum would just be straight down, so it could go out to here and out to there. It's going to move along a circular arc, so you can see the circular arc is here. And the oscillation is simple harmonic motion because it's going to have a set period and therefore frequency. In this case, instead of it being a spring force, because there are no springs involved with pendulums, the net restoring force would be the tangential component of the weight. So, in other words, if you were to look at the pendulum here, because it's only going to have a restoring force when it's not at equilibrium, you look at the weight Fg, the tangential component when you break this apart into Fgx and Fgy would be Fgx. If this is theta, Fgx will equal mg sine theta. This is the angle relative to the y-axis, so this is what we called phi earlier in the year. Anything you see from the College Board on the AP test will probably call this theta. So remember, if you have the angle relative to the y-axis, you need to use sine to figure out the x component. So for pendulums, the restoring force, or the net force, is due to the x component of gravity, so mg sine theta. Period for a pendulum is different than period for a mass on a spring. It's going to depend on length and gravitational field strength, so that's little g. The equation for period is 2 pi times the square root of L over G. So this is the length of the string. This is on Earth 9.8 meters per second squared. So the only way a period can really change if you're staying on Earth is to change the length of the string. If you leave Earth, then the length or the gravitational field strength on the other planet or moon would have an effect on the period. And looking at this, period is directly proportional to the square of the length. So if your length is 4 times as much, your period will be twice as much, and it's inversely proportional to the square of little g. So if little g goes up, then period will go down. And once again, because period and frequency are inverses of each other, frequency will equal 1 over 2 pi square root g over L. You are given this on the formula sheet. You are not given this. So let's just do some quick examples. First, we have a pendulum pulled to the side and release. The mass swings to the right as shown. The diagram shows positions for half a complete oscillation. The reason this is only half an oscillation would go from here over to here and back. So an oscillation needs to start and end at the same point. So for pendulums, it would be from the release point there and back to the release point. This is only half an oscillation because it's only going out. It's not coming back. So which of these point or points will have the highest speed? The mass is coming briefly to rest when it gets to these two endpoints. So if it's at rest here, faster, faster, fastest, slower, slower, rest. So the points where it would have the highest speed would be the bottom of its arc, point C. Which ones have the greatest acceleration? Here, you're going to have no net force because it's in equilibrium, so acceleration will be 0. When you come out here, even though your velocity is 0, it has the greatest amount of net force. So where your net force is greatest, your acceleration will be greatest, so A and E. And going along with that, the restoring force is going to be greatest where the acceleration is greatest, because we know that force equals mass times acceleration, so force and acceleration are directly proportional. So the force will be the greatest at the same points acceleration is A and E. And do one more example. On planet X, a ball on a massless rigid rod oscillates as a simple pendulum with a period of 2 seconds. If the pendulum is taken to the moon of planet X, where the free fall acceleration g is half as big, determine the period. So we know that the period is 2.0 seconds. Your length is constant, so your length on X and the moon is the same. Oops, fine. You're looking for the new periods. This is the period on X. We're looking for the period on the moon. We know that G on the moon is equal to 1/2 G on planet X. Period equals 2 pi square root of L over G. So we can use the period on planet X and G on planet X to figure out what the length is. From there, we can then go back and figure out what the period will be when we go to the moon. So let's isolate. I'm going to square everything. So t squared over 4 pi squared equals L over G. So t squared G over 4 pi squared is going to give me my length. 2 seconds squared times G over 4 pi squared equals L. We don't know what G is, so I'm just going to leave it there as G. 2 squared is 4, so this is 4 seconds squared G over 4 pi squared equals L. 4's cancel. So G over pi squared is going to equal L. So now going over to the moon, T on the moon equals 2 pi square root of L over G. In this case, it's going to be 2 pi square root of G over pi squared over G over 2. It's a little messy. If you're struggling with dividing by fractions, so G over pi squared times 2 over G, that cancels. So this equals 2 pi square root of 2 over pi squared, and this is actually seconds squared. I forgot to carry that over. So this would be seconds squared. So now just putting this in the calculator, we get 2 pi times the square root of 2 over pi squared. This comes out to 2.82, keeps on going, seconds. So on the moon, the period is about equal to 2.8 seconds. This makes sense because decreasing G will increase the period. So it does have that square relationship. I could have also made this much simpler. Because L and 2 pi are constants, we know that T is going to be proportional to 1, or I should say, yeah, so 1 over the square root of G. So T would be proportional to 1 over the square root of G over 2. So on the moon, T of the moon would equal the square root of 2 times T on the planet. This comes out to exactly the same thing. So square root of 2 times 2 seconds equals 2.8 seconds. Either one of these would have worked in this case because the L was constant, but I did want to show you the math. I did want to show you the math for how to do all of this in case, say, L was not constant. That's all you need to know for pendulums. A lot of questions I've seen have just been conceptually being able to figure out what happens to period when one of those things are varied.